Okay. Is my screen visible?
Yes, sir, it is visible.
Okay. Is my voice clear?
Clear, sir.
Okay. Okay. Thank you, the organizer, for giving me opportunity to talk about my research area. But so today is the last day for the workshop, right?
Yes, sir.
Okay. Now, what I want to do is I want to quickly get an introduction from the audience, and because it's like a faculty development program, right?
Yes,
So
sir.
I see quite a bit of number of participants. So I was wondering if quickly I can get to know from people who are here. Uh, I don't think we can cover all, but maybe a representation will be nice to know. Uh, I can see Anu Sekar. You can just like couple of you, if you can introduce where you are coming from and what you do. You can take 5-10 minutes in that, and then we can start presentation. Uh,
Yeah, yes, sir. Sure, sir.
yeah,
So may I request the participants to unmute your mic and introduce yourself to
one
the
by
for
one,
the
just
yeah, one
just
by one. Yes, sir.
right.
Yes.
Yeah, I am Suresh, myself.
Yeah, Suresh. Where
Suresh. So I am working as assistant professor in Rajalakshmi Engineering College, Chennai.
Mhm. Just you
Yes.
have to tell your college and your area of work, or teaching or research.
Yeah, sir. So I'm taking aircraft stability and control, as well as aircraft performance. And so we are handling some projects with the students, like bio-inspired projects. So mainly we are focusing on the low-speed aerodynamics. Sir. Thank you.
Thank you, Suresh.
Thank
Anyone
you.
else?
Anyone else? Please kindly unmute your mic and introduce yourself to the professor.
Sir, good morning, sir. Sir, am I audible?
Yeah. Good morning.
Sir, I am Dr. C. Davamani, Professor and Head Department of Aeronautical Engineering, Mahendra Engineering College, Namakkal, Tamil Nadu, sir. Actually, my research belongs to composite materials, sir. Machining composite material, optimization technique I am involving, sir. So my six scholars are doing in materials only. So that's what I am attending this, sir.
Thank you. Very nice of you.
Thank you, sir.
Anyone else?
Yes, anyone else, please?
Okay. It's fine. We'll start. So, as I can see, people, mostly faculties are here. So the way I'm going to have the presentation is more like interaction rather than having a monologue of continuous presentation where I'm going to continuously talk. So what we'll do is we'll finish section by section and then stop for 5 minutes and then take some questions or discussion. So let's not make it like a question answer session. We'll have a discussion session where you can add, you can put your opinion, and you can put your thoughts and so on. And thank you for organizer for telling me about introduction about me. That reduces my work. We are badly hit by COVID with this current variant, and our campus is having several of cases. So I have to take the presentation from my home, which was completely unexpected. So in between, you may have some interruption, and I'm sure by this time all of us are used to it. So without any further delay, let's get into the presentation. So the topic which today I'm going to discuss is building smart aerospace material using 3D printing. This is our campus, built in 1950s, and we are spread across 2,700 acre with a campus strength around 30,000 plus. Uh, you know, located around 100 kilometer away from Calcutta. Now, and I'm in the metallurgical and materials engineering department. So, historically, when we look back history, uh, the first industrial revolution, and in 18th century when it started in Britain, and textile was the one which was driving it, and it started changing, right? That was the first time when humans started looking industry, and industrial revolution started changing. The farmland started becoming industrialized, and people really understood the potential of machinery. Then another landmark came in 1909 when Ford, who is one of the leader in America for his uh, remarkable work in different area, but he's the one who came and he said that, look, if you can build things for every customer, and when he said things, it means car, right? And he's the one who came and said that, look, we can have car of different variety, different color, and different interior or electronics, now we can say today. But he started talking about customizing cars and putting them different colors for different customer interest. Now, till now, the car used to be just one color and one design. Now they started changing. A lot of changes happened, and that's where uh, the second industrial revolution came. And today we can see that we have in every segment we have so many cars, so many variety, and every other 6 months now every car company need to update their cars and so on, right? So that was the second revolution. The third is going to be a manufacturing uh, change or manufacturing landscape, where we are going to change the way we build things. Now, again, it's not very easy to completely change things, but again, people started looking at the third big revolution, and that's definitely is not going to be conventional, right? It's going to be away than what current things can do, or what current industry or manufacturing can offer. Now, conventionally today, the subtraction is what people in machining, they are continue following it, milling, drilling, cutting, CNC machining, and so on, where they generally cut down things, right? Now, it has its own advantage and disadvantage, but the current trend or the future people are looking at is, without wastage, how we can build things, okay, and how we can reach to the complexity, or what are the things which we can build which was impossible till now. And that's where additive manufacturing comes in, uh, where people started building a solid object by putting materials rather than removing materials. And we'll try to touch upon, because most of your faculty, so I'm not going to talk too much basic about it, but yes, we'll discuss a few of the key issues which I think we should discuss before we get into the research area of 3D printing. Now, uh, again, 3D printing can put any shape and any form and so on, right? And there are several technologies available for 3D printing, and this is one of the most interesting area where people are moving in both direction. One, we are moving to build bigger and bigger 3D printers. Also, we are build, and there are several companies and several agencies who are building printer for school, right? So this is a very interesting technology which I can see both the direction it's moving, and it's reaching out both the sides, right? So tomorrow, suppose the companies are going to have 3D printer as a manufacturing, remember, it's not going to be new, as like in our generation and previous generation, where you have to go to degree colleges, engineering colleges, or training schools to really know the machinery. Whereas today, you think about 3D printing is already reaching to schools, so the school kids already they know that, okay, there is something called 3D printing, what is the basic, and so on. So it's going to be very interesting. Now, as I just want to have this slide as a, just, I'm sure all of you know, 3D printing is nothing but putting things layer by layer, uh, taking the computer model and really making them realistic. Now, that's a big change, right? Because if you go back and look at conventional processing, what you see or what you imagine, and when it comes to reality, there are multiple steps, and there are several error and several human involvement, and today if you want to just get a machine, right? It's not just one step. You have to really get through the every measurement, designing, and so on. But 3D printing has changed completely the whole way of manufacturing things or building things. And today, if I want a screw, if it's there and or I want to replicate it, I just put a scanner, scan it, you get a computer model, and then just press print, and then what you get is the printer prints for you, and then it's going to be precisely as you expected or what you designed here. Now, not just that, you can build anything what you can design in computers, and we are going to see some of the interesting examples. But again, uh, having said all about 3D printing and excitement, uh, it's going to be continuously a challenge or a process of evolution where we are going to meet this triangle. And triangle is speed, price, and quality. Okay, it's very difficult to attend all of them together at one place, right? Always it's a give and take of one or the other. But with 3D printing, people are projecting that it will be possible some point of time to achieve all three together. And again, I will not say that it's already done. We are in the process, and there are challenges involved, and we'll discuss some of them in the current presentation. Now, just to excite you and talk about 3D printing, I'm sure the speakers before me, they have introduced it. So I'm not going to spend too much time. I'm going to briefly talk and just make you excited before we go deeper. As I told you, 3D printing can build any shape, complex parts, or it can be produced by any shape, any material. Also nowadays is coming into picture. Uh, Anything what you produce in computer is essentially can be printed, and we can realize it. We can make it customized and personalized things. It can be jewelry, it can be fancy things, or your art stuff which you are keeping in your uh, in your decorations and so on. So all these personalized can be done, and it's a big portion of 3D printing which people are utilizing it in that area. But yes, as I told you, there are list of challenges, and it can be even longer. But I'm just going to quickly tell each of them so that we know what are the challenges it's going to face. Now, the first and foremost is cost of material. Okay. Now, you know 3D printing is a technology which is developed by a mechanical engineer or instrumentation guys or production people who are building the equipment. So equipment, and there is a major role of computer and automation and so on, right? So the combination of these two has built a fantastic 3D printers. It's all over. Today we can buy printer all the way from couple of thousands to several crores, and it can do fantastic job. But whatever you are going to make in realistic, it is come to a point of materials. And when it comes to materials, the cost of material is crucial. Now, the 3D printers or every printer you build has certain requirement. It cannot just take any shape or any form of material. You need to process them. Now that adds to a huge cost because we are going to post process a material. You cannot just take a rod or a slab or a certain shape and start making anything out of it. You need a material of certain grades, certain purity, certain shape, and we are going to discuss that. So that brings additional cost. Unreliability of machines, right? Now again, it comes to a material as well, or the understanding of material. When we 3D printer, shape, structure, everything remains same, but materials and its defect, which is formed during processing, have a rejection. It means outer diameter and everything will look precisely same. It will do the job, but when you go to microscopic level, you end up having porosity. Okay, it can be 1%, 2%, but remember that's a lot for some of the industry. So there are huge rejection in certain industry. Uh, Challenge in scaling up technology. Again, in certain cases, you do see the printer is working fine for certain size, But the moment you start building bigger and bigger, you start facing problem in terms of interfaces, in terms of its purity or defect-free structure, and all these comes into picture. Speed, although 3D printing gives you opportunity to print anything and everything, but if you want to achieve certain quality, speed is an issue. IP is a big issue here, and I'm not the expert, so I'll not talk too much. But yes, intellectual property or patenting is not that easy because the science of it is already known. The basic behind it, it's well established. So if you develop something, owning it is difficult. Also, conflicting IP is also very common, and we'll have one slide doing some of the processing. You end up putting some chemical, or it ejects chemical, which can have some environmental aspect. Surface finish, although the dimension or macroscopic dimension is fine, but surface finish is always a balance between speed, cost, and the material what you're using. Achieving a quick or best surface finish is a challenge. Resolution. Uh, we can print macroscopic object very easily, but when it comes to a resolution of some micron, we are 3D printing is still have not reached to that limit. Mechanical properties, which is connected to the defect and all, yes, every part looks similar, but when you start testing, there are deviation you clearly see in every part. So that is again another thing people need to see. Post processing, not every printed parts can be post processed. So if you need a post treatment of 3D printed object, it's still a problem. And currently people are still focusing on shapes and just on the, we are just initiating the whole technology we talked about. We have several things to explore, and I think it's emerging technology which is coming up. I told you about the intellectual property, and just because with 3D printing you can replicate anything and everything, that brings to a several IP conflict, because now nothing is proprietary. Whatever today you buy something from any other part of the world, you scan it and then you can start reproducing. So that puts a big threat to the existing technology, and people are in the process of trying to solve it. But yes, it's going to be a challenge. Cyber risk, yes, because remember, 3D printing is connected to computer, and when you talk about computer control machines, if someone is able to control your computer, he can control your whole processing. So that becomes a big risk. It's not just machine, or if someone is mechanical engineer or structural engineer, and they just understand one part, they don't understand computation or computer capability, it's it's a big threat, because you have to understand that as well so that you can protect your machine. So hacking, cyber risk is and all those software related issues are common here in 3D printing. Liabilities, yes, it's already we discussed about it. It's going to be a problem for quite some time till we really optimize and set everything. Uh, Connected to that, remember when we talk about some of the technology where we try to make very sensitive parts, it can be aerospace, it can be medical. Uh, it's good in one way, but we have to be always careful not to use in a counter productive direction, and people need to certify them, and there need to be a certification before we use. Otherwise, anyone and everyone can start making things and so on. There are several cases where people printed guns and so on, and those kind of not very productive way of doing things also happen. So that is a big concern with the 3D printing. Quickly, we'll move to the next thing which need to be, I thought it's a good idea to discuss that with the myth and reality, right? So uh, we'll have a couple of points. So first is the 3D printing. It's very common. People say 3D printer costs too much, right? And I'm sure all of you are aware that it's not, there are printers which are very expensive, and they are a couple of crores and maybe tens of crores nowadays. But you can buy a 3D printer as cheap as 20,000 and so on in Amazon. You can find a small printer which you can connect to the computer or whatever electronics you have and then print them. So reality is 3D printers are cheap as well, and for training you can use some of them. The next myth is 3D printing can print only plastic. Uh, it was true initially, but now with the current technology, and yes, we are evolving, and the community of 3D printing is trying to evolve. Now it's not just plastic alone. People are able to print metals, wood, resin, carbon fiber, biomaterials, food, concrete, and the list goes on and on. We are also exploring this direction, and we have some work in this area. We'll discuss that. But yes, this become more material problem where people are trying to see how we can utilize printer to print any material or every material possible. uh, uh, yeah, there are all sorts of news. People talk about 3D printing can print human organs and so on. And the reality is, yes, people are doing research in this area. There are several successful examples where people are able to print organs, but it's not that trivial that everywhere we can just print and use it. So still area where people are working on. uh, Another myth is, the very common perception people have is 3D printing can make very quickly whatever you want, right? Now, it's not true always, right? Suppose I have a metallic block and I want to cut a square. Versus I want to print a square in a 3D printer. Now, machining guy, you go cut them all the faces and then you have a cube. Whereas 3D printing is going to build layer by layer and it's going to take its own time. So in 3D printing, if you have a very simple shape which you can do by normal cutting or simple machining, it's till now it's not going to compete that directly. So it's not always that 3D printer is quicker. There are cases which it can, but not every. Uh, another another myth all over we hear is every home will have 3D printer soon. And yes, the simple model or the training model can be there, but remember those are only they can print object like simple plastic and so on. Still, and even the fillers what they use, it's not that cheap that you can buy every week and so on. They are still in the little expensive range. So it's going to take a while where every company or every manufacturing unit will have its own 3D printer to build things. Because still the process of universal printing or printing any object is not there. So it's going to take a while before it is there. Another myth is all over that 3D printer can make things cheaper, right? Remember, yes, the machining cost or the human cost is not involved, and there are no human involved, so you don't really pay for the salary or wages. But remember, 3D printer does have a cost, right? Uh, One is the, your printer cost. The second, building things in computer, right? Although you can scan and get things, but remember there are human involved where they are going to build things in computer before the print. Also, the checking and making sure things are happening. Still, the humans are involved. So it's not always 3D printer is going to be completely man-free or is cheaper. It's going trying to go there where it can be as cheap as no one touches it in large scale production. But if you want to make customized things, you do have to have certain number of people who can build things in computer. uh, 3D printing is for large scale manufacturing, and that is another thing which people generally very commonly say that, oh, he wants to build several things or multiple number using 3D printer. In few cases it's right. If it's very complicated shape, making them several of them is going to be less time consuming or more efficient. But remember, if it's a simple part like rolling, flat slab or a simple object, you don't want to use 3D printer to build them, because that's first is going to be time taking. Also, it's not going to be that useful. So 3D printer is always for very customized and specific thing, which you cannot make by normal methods, or something very specific you want to use very specific material. There also you can use. But again, this is a process which we are evolving. But what I'm talking about is what we have done so far, or what 3D printing has been able to do so far. Uh, a quick trend and development, multi-material 3D printing is something people are looking at, how we can print different materials. So today you have a metal printer or plastic printer or ceramic printer. Now, can we have all different materials, putting them together and we can print it? Can we have a component where you have a metal and plastic and we can continuously print it? That is something which most of the 3D printing or printer build, the community who is building printers, they are trying to do multicolor 3D printing. And with that, what it means is, can we have one component where you know each area or each strand is printed in different color? That's another area of research people are doing. The next is how we can print things faster, better, larger, and easier. So, if you look at the printers 5 year back, you need to have a good computer with certain computer capabilities. Today, the same printer you go, and they will have something like printing using Wi-Fi or Bluetooth, or you can. They have a very small software which you can even use in your phone. All those feature has come, and people are moving in that direction. How we can make the printer faster, how we can make it better in terms of resolution, capability, larger, how large we can print. People are talking about printing houses and so on, and easier. Like, you don't need a sophisticated computer or high capability computer. How we can print things with your smartphone or tablet or handheld devices. 3D modeling is a big component where designing those things using uh, conventional design tool like AutoCAD or CAD/CAM, SolidWorks, and so on. They're heavy software, but people are trying to replace them with a software tool which can be easily done, like app-based and so on. That's another direction where a lot of work is happening. The new application area of 3D printing is always there. People are looking at niche area where 3D printing can contribute as compared to the conventional processing. So that's always area. Every time you come, you see the news, you do find people have utilized 3D printing for some new application. It can be batteries, it can be sensor, health, space, all over, right? So every time they are looking at newer area. uh, Improvements in metal printing, because metal is a structural and most of us do use a lot of structural components. So improvement in metal printing is a big community. There are journals where they just published things related to metal printing. 3D printing buildings is a big area where people wants to print smart houses or more sophisticated or well equipped houses with a cheaper cost and newer material. Uh, and that's the area where material scientists like us, we are exploring, where we try to see how we can print new material which has not been possible by previous research. So these are the different trends and development which has been so far. And remember, I'm not going to go very detail of all this because we have to get into the research area. Yes, multi-material is one. Then we have metal 3D printing we discuss about. People are able to print normal material like aluminum, steel, brass, and so on. But the question is how we can print combination of these two or alloys of certain composition. And we'll come to the research section where I'm going to discuss that. Building, yes, we are trying to build mud, resin, plastic houses, complicated houses. And one of the interesting area recently, NASA, they're talking about that they are going to put 3D printers and they're going to build buildings or structure on moon or Mars and so on, right? Where you don't need to humans are not involved, the printer will build things already. This is a fairly advanced stage. They are already And any conference you go, you see things like this where the whole car is printed using 3D printer. There are several companies who are already in a very advanced stage they are talking about, but yeah, always it attracts to see a big car or this kind of component already printed by 3D printer. Now, I think we had a long introduction, but this is just a curve I wanted to attract your attention. And before we move into research direction, in y-axis we have expectation, and next we have time. Any technology, uh, when you look at, it's a good idea to put in this plot, right? And generally, the technology follow this path, right? And this curve is divided into several subsections. The first is innovation, right? When I say innovation, what it means, something comes up new. It can be a new material or a new technology. People really get excited about, and you can see several things can be done, right? So this is upward curve. With a very short time, it builds a lot of expectation. Okay. Now, if you see 3D printing, they have this technology which is called 3D bioprinting. Okay. So 3D bioprinting, which started say a couple of years back, it is in the stage where they are able to show.
Daddy! Daddy! Excuse me, sir.
Yeah.
Yes.
Okay. So okay, just for the audience, I know all of us are in house, so don't panic if you have someone is unmuted or kids are coming. Let's make it informal, okay? It's very common. It's okay. So even organizer, don't panic if someone mic is unmuted or some background comes, because this is part of our current situation. Okay.
Sure, sir. Thank you.
Yeah. So 3D printing is a system where we are having a lot of excitement, and every other day we are hearing about that. So this is the expectation stage. Then comes peak, okay, where we realize the invention can have anything and everything possible, and that is where the highest expectation reach. And then comes, this is called disillusion. What it means, we start realizing what are the limitations. Okay. And there are 3D printers here, you can see, which is in the stage, and that's consumer 3D printing. When I say consumer 3D printing, means the cheap 3D printer what you have around you. When I say cheap, means cheaper cost, right? Like 20,000, 30,000 printers, they are flooded in the market. Every other company is building it, and they are trying to sell it. Now they have reached to a limit where they can do X, Y, Z. So you go to the market and try to buy a printer, you see it can do certain things, right? And that is where you started having your disillusion. It means you start realizing that, oh, it can do only certain things. Same thing goes with technology also. You start realizing, oh, this technology is great, it can do several things, but it can limited to only those areas, right? Then comes a slope of enlightenment, where people start realizing, okay, it has limitation, it has a lot of excitement, but if we engineer them and put them nicely, we can do a lot of things. And this is where a lot of engineering thing happen. Again, 3D printing is here as well. The industrial 3D printers are in this scale, where people are able to utilize them for certain requirement. And then come the last uh, part, which is called productivity or plateau of productivity, where you reach to a saturation and it's going to follow. Now, I put this to just show you that 3D printing is in all these three sections. Okay. Uh, and what I'm going to do is I'm going to discuss more about this area. Okay. And what are the challenges, why, how we can build things, and this area where we are building things. Okay. Being an academician, it's always good to be in this area where we can excite people and show things which were not possible. At the same time, being an engineer and being in an engineering department or engineering researcher, it's very crucial that we solve some of these problems. Okay. so that we can see the plateau of productivity. With that, let's start the first part, and I'll just take 1 minute break. I just need to drink some water. Just hold on. Any questions so far? By the time we can take questions.
Yeah, the participants. I request the participants to post queries in case if you have any queries in the first half of the session. You may post the queries in the chat box, or else you can unmute your mic and you can talk to the professor.
Yeah, anyone, if you have a query, you can unmute yourself and we can talk. We'll have 5 minutes for the question.
Hello, sir.
Okay, sir.
Yeah.
Hello, sir.
Yeah. Vairam.
Sir, just I want to ask some questions, sir.
Yeah, please go ahead.
Myself, Vairamuthu. I'm working as assistant professor in Parisuttam Engineering College. It's Tanjavur district.
Oh, very nice.
So it's so actually the session is going very nicely, sir. I'm learning more things from you about 3D printing and how it is using for our industries and other industries. So just it's simple questions from my side. Is there any limitations to what shapes, sizes, and we can take the 3D print, sir? It's some criteria will be there, Leila.
Okay. That's more research question. So the next section of the slides will show that the possibility, certain, like depending on resolution and the kind of printer you have, and but in terms of shape, whatever you can create on the computer, you can print it. Okay. Anyone else? I do see some chat messages. Just hold on. Let me read it out. Okay. I thought there is a question. Okay. Right. If you have any question, feel free to just post in the chat box. And once this second portion of the talk is going to get over, and we are going to spend some time again to discuss the question. Okay?
Yes, sir, sure. If there is any more questions from the participant side, please unmute your mic and talk to the professor, or else you drop a message in the chat box, please.
Okay, fine. So it's nice that we got this question, which sets up the tone for the next set of slides. Okay, and that brings to a very interesting story all around, or evident, I'll say, or incident around us, right? If you look at around you, what human builds is always flat, right? Our walls are flat. Our things like table, your laptop also has a very flat shape, right? But when you just step out of your working table or your house, you look around yourself, right? How many flat things you observe in nature? It can be tree, it can be flower, it can be leaf, anything, right? Nature never builds flat things, right? Look at yourself, right? In our body, we don't have even it's very hard to find a flat thing in your body, right? Always there is a topology, curvature, right? And there is a shape for everything. It's people have the evolution guys, they talk about shapes and so on, but when it comes to engineers, we never talk about that, because the reason is we can't build things, right? And if you can't build complicated things, you cannot understand, right? That's the first thing comes into. Now the question is this complicated shape, and the first example I'll take is seashell. I'm sure all of you went through ocean and see this seashell around you, and if you look at seashell, there are all shapes and morphology and topology available, right? And And it's very interesting that, remember, these are not built by humans, right? These are built by a very small species. And interestingly, they build so complicated thing, right? And they're building by bottom up approach, right? There must be some reason to have such kind of complicated shape, right? Now we'll try to come back to here, but let's look at macroscopic level and look at this. This is a pattern built by river, right? Now, the flow of the river, it never makes things flat, right? Look at the curvature, right? And this is the picture which is taken in Grand Canyon, where the river makes this kind of pattern. And you can see the topology all over, right? Now, the Seashell topology has been utilized by the evolution guys. They try to understand the age of the seashell, try to understand the depth it can form. A lot of geological and ecological observation has been made by this seashell shape, right? So it's not new. In structural engineering, this kind of topology shapes are explained a bit, and people do have several observations. But it's very interesting to see that, a very unstable structure. And if someone is making house and so on, they will not like to have things like this, right? Where you have a floating stone and so on. But if you go to mountains and hills, you'll find these kind of stones are stable for hundreds of years, right? And nature choose this kind of equilibrium, which is not well defined or not, flat shapes, right? It has topology. Now that excites us, and being a material scientist, the seashell, we came back and we look at seashell, the inner structure. Okay. Now, if we break the seashell and look at under scanning electron microscope or AFM, what you see here is the layered structure, right? At lower magnification, when you zoom out and try to see, there are builds like this, right? Now, it's very interesting to see ocean living species, very small, can build beautiful nanostructure like this, right? And Necker cell is what material scientists or the materials engineers who are working in this area, they call it. And if you look at the length scale, these are like 1 micron plates which are stacked on top of each other, and in between they have a organic or soft molecules, right? Thin layer of that which is separating them. That excites a huge population of scientists or huge crowd of scientists who end up exploring it, right? And a large amount of research has been done. If you look at this nanoscale structure and try to look at macroscopically, and you go to old mountains and so on, you'll find a nice similarity. You have a ceramic plates and they are separated by organic, right? Now think about nature build things which has scale independent, right? And we'll come back to this example where we are going to mimic them. But let's discuss the first question about seashell. Why even we have this complicated shape? Now, 20 years back, if you talk about seashell and try to say that can we make them artificially, the answer will be no, right? Because we cannot look at the shape. And just to give you, we choose two simplest seashell possible. The first one is this one, what you see on your screen, right? I'd just like to highlight the two simple complexity, or I'll say three simple complexity in these seashells. The first one is it's not spherical. Okay, when we draw anything, we build anything, we make spherical, right? But it's not spherical. You can see, right? The edges are not flat. You can see they are not flat, right? It has a shape and one particular region, and that is where the two seashell parts are joined, right? And it has a complicated feature. And third one is you see the surface is not flat, and it does changes. It does change depending on age, right? Now we take one seashell, scan them, and then build the computer generated structure, and the same can be printed. Now, this is complicated, but this whole work was done in 2015, where we built the first 3D printer in our lab, collecting each component and putting them together. Putting this computer generator was also not easy. It has several challenges, but today you can do this whole thing in just 5 minutes. Okay, in our same lab, you can do this now. With a nice scanner and good software, it can be done. But in 2015, we were able to print it. Same goes here, although it looks very simple, but there are few observations you have to make. The diameter changes here. And also you see they are not flat, right? It has a smaller to higher diameter moving from here to this end. We took it again and then we can print it. Now we have printed this, we can understand why the seashell or the living species who is living inside this build this kind of shape. We move to computer simulation, and thanks to several advanced tools which is available to us, we can understand mechanics of it. Now, if you take a conventional hemispherical structure and apply stress, what you are going to see is the stress distribute all across uniformly. Now, we add the first complication, which is the core sort of spine moving across. And if you apply stress, what you see here is localized stress or strain distribution, right? It's not uniform like hemispherical. That explains the first question, why the seashell has this kind of spine. Now, moving the third level of complexity, which is putting this kind of curvature on top. And when you put this complication and run the same simulation, what you see here, this particular feature creates convex and concave surfaces. So we have a positive and negative surface next to each other. That's again helps in changing the stress distribution. Now, this explain, and I try to be very simple in most of these cases so that everyone can understand, but we can always discuss very specific thing involved into all these research work. Now, this is a very simple thing which we understood now, but in terms of if you want to understand how the living species build things like this complicated shape, what we do is we put an aluminum plate below, assuming if a living species is inside it, how it's going to see. Now, first is the hemispherical or object, and if you look at the aluminum block, the stress is distributed all across. But if you put this spine, and this is how the stress transfer onto aluminum block. If you turn around and see, there is a region where there is no stress at all. What it means, if you stand here and someone presses on top, you will not face any stress. And that, that tells us why the living species build this structure. Now, putting the third topology, again, this region remains same, but the localization on the edges changes, right? It means if the stress crosses the certain, or the load crosses certain limit, still it's going to be protected as compared to the previous structure and the conventional structure. One interesting observation was why the thickness changes, right? And we see the maximum stress and minimum stress changes if you change the complexity. But the thickness also changes the distribution from maximum to minimum if you increase thickness. And what we see here, the optimum thickness is 1 millimeter, where it can protect the best. And as the cell grows or the living species grows, the cell thickness increases because they don't need that level of high protection. And remember, the seashell thickness is utilized by the evolution guys to predict the age of the living species or the shell or the earth crust and so on. So the thickness is correlated to mechanics as well. We do explain the curvature effect and with the analytical model that if you have this kind of curvature on top, it's going to have a huge stress distribution. So if you keep on adding this curvature, if it's flat, it's almost nothing happens. The stress transfers from one to other. But if you keep on building this, the distribution increases exponentially. When we come to the other structure and try to compare with cylinder, the same thing we observe here. If you apply stress in a cylindrical structure, okay, we do make an assumption that the radius increases from one end to other, but if you apply stress in one of the corner, it transmits quickly. But when you add the hollow structure, that changes. But if you put this particular structure and if you apply stress here, it really, or any one of the edges, it really doesn't transfer. Very similar to the previous case, it has the similar thickness effect. And when we do real testing of the seashell and the 3D printed shell, what we see here is, assuming a flat object of similar surface area, it can take much lower load as compared to the 3D printed complicated shape. In both the structure, the same we observe, that if you give this kind of shape, the load bearing capability increases. And we break the material till fracture and try to see that why the certain region fails over other, and we try to match with the simulation. What we see here is, if you take the seashell and try to crush using leg, the first thing breaks is this particular edge, right? And remember that the living species is going to live here, hence it's not going to face any stress while if you try to crush them. And that's exactly what we see in simulation. The certain region breaks over others and other region can be protected. The same thing happened in this particular structure where, remember, the living species tend to stay into this particular region or they can move easily. Now suppose by exterior stress, this region feels a load, and then the living species can easily move into this region and protect themselves. It's a very simple example. The work was done way back in 2015, but we can extend this to more complicated understanding by building things and testing it. And we add to the next complexity, and aerodynamics or space exploration is always inspired by bird and species, right? Now we in our group, we started going down and start looking at some of the beautiful things which is built by the small species ants, right? And in India, wherever we go, you can see ants are all over, right? Now, one of the interesting things about ants, if you see on top, on the surface, this is how they look like. Okay, there's some hole and bunch of material, right? But if the soil scientists or geologists and all those people, when they do a lot of exploration, they see ants builds really complicated ant hill, right? Or ant houses. They are connected, the shape is complicated, and there are beautiful architecture available. You can buy it, you put and what they do is they pour metal into this, and then they get this ant mount or ant hill houses like this. They are beautiful in terms of decoration. But the question we wanted to ask, why really this small species like ant build this complicated shape? Now, taking this complicated shape and trying to build individual building blocks is not easy. So what we did, we took several of these structures and we pour cement into it. Okay, the liquid cement, so that we can retain the shape. We pour the liquid cement and let it cure. Once cement is cured, we get this structure, right? Take the structure and do a 3D scan. You can utilize CT scan or even normal X-ray scan will do, and then take the 3D scan file, build it computer model, and print them. Okay. Now we picked up 4 different examples. The first is the very new anthill, where what they do is they just build a small, center is smaller, and then where they enter is bigger. The next complexity they add is they make another house, right? So they make connected here. The third complexity they add, they extend it with a different variety of diameter. And the fourth variety we choose, the both of them grows, and one is bigger or one is more, one is having more topology versus other. Now, these are the 4 building blocks we chose. Again, it can be several more, but we restricted to 4. And then we try to understand what really happens in terms of deformation. Again, the computer simulation comes into picture because you have already built the model. You can easily do all sorts of deformation study. The first study is point load, assuming that someone puts leg onto their top of their house, or something is moving around, it's going to press localized stress. Now, so for that we do a point load analysis, and what we see here is we apply load here and look at the stress distribution. Now you can see either you apply load here or here, because the topology is complicated or complex, the load doesn't transfer or the strain doesn't transfer. So if ants are living in this area and this area is deformed, they're not going to face anything. Other way around, they can easily move and save themselves, right? Same thing if it's broader base and this is getting more complicated, you can see rather than transfer from here to here, it's just going to localize on top itself. If you have a two different directions, you can see if you are applying load in this, the other is completely unaffected, right? And if both of them are, if you have multiple housing, you can see if you apply a stress, the only weaker region can break, whereas other region is just going to be unaffected, right? Same thing we can look at. So this is strain distribution and this is stress, or one might say stress. And you can see the stress is really localized just because of complex topology. It cannot transfer even to the next region. And that explains the first question, that ants has this topology to protect themselves from exterior point, right? Point load. The second issue can happen is uniform pressure. It means if there is a small ant hill and people are walking around, right? And the soil is not very steady. What's going to happen? The soil around the house is going to move, and that is going to create a uniform pressure. What we do is we run the simulation again with the uniform pressure, and we can see very similar observation. Although there is going to be a surface small deformation, but interior is going to be unaffected. In all these cases, very similar to the point load, they are going to be localized deformation for certain region, others are not going to be affected. I'm not going to discuss all the detail because we are really running short of time. So with this, we are able to perform experiment as well and try to replicate same thing. We have done the point load and the uniform stress, and we can clearly see exactly same thing what we observe in simulation. We also observe, depending on topology and the morphology, it can take a huge amount of, or it can absorb a lot of energy before it breaks. We do see a good agreement between theory and experiment, and rest of them are there in the paper already. Moving ahead to a little bit bigger picture to talk about this whole area, just to give you a summary. If you are interested, you can read the paper published in Materials today. Any engineering design, when you are making material, this is what you see, and this is strength versus density. And what it means, if I map all the, and this is ASB map, we have taken it. You look at all sorts of material. It can be foam, wood, plastic, metals, alloy, ceramic. The density increases if you want higher strength, right? So you want ceramic or metals having a gigapascal strength, you are going to make it heavier, right? Plastics having lighter density, but it's going to have it's going to have lower strength. And that continues, right? There is no end of it. But the point is, which is the ideal engineering material? And it's going to be this particular region where you have lower density and higher strength. Okay. Now, if you want to build this material, so far this whole area is empty, right? In the future, engineering materials are from this region. Okay. But building this material or this kind of material by conventional method is not going to be possible. So what you need to do, you need to create porosity such a way that you reduce density. So I take metal, alloy, ceramic and create porosity 50%. Okay, that will bring here, but I create those porosity in such a way that the load transfer or the stress doesn't affect it. Okay, and that will change the whole way how you build things, right? Now, so far our group works in these 4 way of doing it. One is we look at bio-inspired structure, what you saw just now, okay, and try to mimic them. The second is we look at microscopic scale building origami and so on by conventional what is already there. The third is we create a lot of models, okay, by selective removal of material and see how we can do that. And the last is making atomic scale and try to replicate it and build the structure which are porous but it can take load, okay. The summary of the paper, I'm not going to talk too much detail, and you can read it because I have to quickly move ahead. There are several origami, kirigami structure which are very useful for space, where they can put things which can fold, like which can fold, unfold with a control. It can be a thermal control, sound control, or any other exterior or remotely controlled method of opening or changing its shape. So that's one of the way they look at, and the huge research is happening. These are mostly inspired, they call it, by Japanese art, which is called origami or kirigami. You can read more detail into the paper. This is an example where they build this structure by heating and cooling, it can change shape. Okay. uh, Again, very similar to that, we have a cutting these material. So building is origami and cutting them is called kirigami. So you take a piece of paper, cut them in such a way that it can take much higher strain, or it can elongate heavily, right? So if you take a piece of paper and try to pull them, you can just pull them, say 10%. But what you do is you cut them, right? And then you try to pull, you can see you can really make it big. Or you can fold these objects and cut them locally, so that a plain paper or plain paper looking like can change into different shape. Now also in space, when you talk about, when you're putting things into space, you need things to be compacted, but when you are going to use it, it should expand, right, with a control thing. And all these areas research goes into that direction. uh, uh, you know and most of these are not just limited to structure, these are going to be utilized in different area. It can be architecture, it can be biomonitoring, sensing, it can be tissue engineering, it can be catalytic, and so on, okay. I'm going to discuss about some of the structure today. I'm going to show the complexity we are able to print and we are building, and also observing its mechanical properties and so on, okay. uh, and at the end of the day, you will see that most of the structures are going to be beyond what is already there into the literature, or what is there in the use already. You can see the paper which took the cover page of materials today, and we were talking about topologies, engineer structure, protecting the all our structure on planet Earth, and so on. You can read it; it's there already available online. Now, moving next, and this is where we are going to talk about some fancy area of exploration, where we are going to talk about utilizing nanoscale structures to build complex structures. We'll, if you have any question, we can take up a question quickly.
Yes, sir. Thank you, sir. Okay, participants, before moving to the next topic, I may request, in case if you have any question, you can ask.
We'll move ahead. We can take up the question last.
Yes, sir. Sure, sir.
Yeah. Okay.
Yeah, sure.
So, carbon nanotube was one of the initial nanomaterial which people were excited about. And when you take a nanotube and try to do mechanical property measurement, what you see here is the flat nanotube is fairly softer than, if you have a complex topology like X geometry, Y geometry, or I'll say interconnected carbon nanotube geometries were much more stronger or stiffer as compared to a simple nanotube. And the reason was the topology in the nanotube. Now remember, this topology, when I say, means curvature and this kind of complexity in shape, is because of atomic scale defect and atomic scale bending, right? And the MD simulation does show that. Now the question is, The simple carbon, which is hexagonal geometry, if you create this kind of defect and complexity, can have such a huge effect into mechanical response. Now, can we take carbon and build a structure which is as complicated as is shown here? That these are all 3D. I'm not going to play the movie because it's just going to take a lot of time. But see, these are built by a German scientist, Swordzides. He took carbon and built these complex shapes. Now you see the complexity of shape can be explained in just one word. You cannot have a single point where you have a flat surface. Every point is different topology or different plane as compared to one. These are really complicated in terms of 3D. What we have done is we took this simulation, it took these structures and then printed them. So these are atomic structure, these are computer model, and these are printed. And what we when we do mechanical testing, we see a huge enhancement because of this complex topology. The details are in the paper. You can read about it. There are a lot of excitement in terms of porosity control or local deformation in all the structure. Just to give you a right perspective, the mechanical property of the polymer which is used here is PLA to demonstrate the effect here. What you see is more than 10-fold as compared to just simple block, right? So if you take a 3D printed block and take a solid polymer, just by creating this porosity, it's not just we retain the strength, we reduce the porosity, hence we have a huge improvement in specific strength. And specific strength, when I say it means strength divided by density. I'm not going to go into detail. We are really running short of time. The next challenge is building, wherever the army, they call helmet, bulletproof helmet, right? And yes, we have been able to build successful bulletproof helmet, but the problem is most of them, the moment bullet hit, it can protect. But a detailed simulation has shown that the impact on human, although the bullet doesn't hit, but there is a force or impact on the brain of the human. Hence, after some time, they start getting several health issues. Now, the question is, can we build structures which can not just stop bullet, it doesn't allow the load or stress also to transfer to the human inside. And we move to more complicated structure, which is tubulin. These are little denser as compared to swordside, but they are even more complex. And the topology is again inspired by a tubulin structure, which are at atomic scale. We make it macroscopic scale. And that brings to the question of Maker, if you remember Seashell, trying to build things at nanoscale, right? And the other side, you look at mountain and hills, they are very similar pattern. Similar analogy we are using here. We are taking atomic scale, replicating it at macroscopic scale, and we do see the enhancement or effect of topology, what was observed at atomic scale, can be replicated at macroscopic scale. So we print different structure of tubulin, and then we do the mechanical testing. There are several interesting observations already reported in the paper, but one of them is the specific energy, how much it can absorb, also the directional deformation. So as compared to a solid block, these generally they deform in a certain direction, not just and which is again explained with help of MD simulation. We can talk about why this topology or the complexity helps in the load and strength transfer. But one of the key issue here is the high impact load. And so we have tested the object with a 5 kilometer per second speed impacting, and then we do the these are the top view. But when we do X-ray scan and try to see the load, how the transfer, if you have a solid block, if the bullet hits, what happens is, although the bullet stops here, but you see cracks all over. What it means, the object here, assuming your head, when you hit it, it's going to face the heat. Because you do have cracks, it means the load or strain has transferred all across. Whereas the 3D printed tubulin, although it deforms on the surface, very similar to the solid blocks, but you don't see any deformation at lower part. Most of the stress or the strain get localized in this particular region. The quantity plot also shows the depth of penetration, damage area, and volume fraction change are way lower in tubulin as compared to solid. So it's not just mechanical properties you enhance, this kind of impact loading enhance. The simulation also shows, because of the local the topology and the heat which is utilized to absorb the crack and doesn't crack transmit from top to bottom, and related phenomena helps to stop the high impact load to transfer at the bottom. The details are there in the paper. You can go through and see it. Because of the excitement, the paper took the cover page in small. This builds to the future helmet. It can be your bike, it can be your sports helmet, or it can be military helmet. There are a lot of work we are doing in collaboration with military, but not just military. It can be used in our conventional helmet where we can flow air and make your helmet cooler. Just a sec. Okay, so that we can make our helmet with a similar mechanical performance as the metallic one, but it will have several other effect in terms of thermal and these kind of unique properties. These 3D printed blocks can be utilized not just for mechanical, it can be used for water treatment. And in one of our work in RSC Advances, we show that nanoplastic can be cleaned with the 3D printed blocks. If you choose the printing material very oppositely charged as compared to nanoplastic contaminants, and what will happen, no physical filter can really separate plastic, right? Because nanoplastic, because of the reason you can't really make nanoporous structure which can trap it, right? Whereas if you have a charged surface and try to print them into a large surface area, it will provide a lot of oppositely charged surfaces where the plastic can go and get absorbed and treat the water. This was the first work, so it's a very preliminary work, but now people have started exploring it in a larger detail. Also, we can utilize this template to coat some of the material which can treat water and clean the environment. Not just water, we have also started working in catalysis area where these these surfaces will be utilized to put catalyst so that we can store the catalyst and keep on the reaction can continue. In general, if you put those powders and in high air flow, they can go away. Whereas if they are coated and binded on the surface, they will remain there. They will not contaminate water, rather than they will treat the water. The details are already there in the paper. If you are interested, you can read. The next challenge is building 3D printer structure with a local deformation, right? Now, for example, if you have the front of the car, right, and if you take a solid material and then when it hits, it's going to transmit the load. What you want in some of these this kind of parts, localized deformation. You would like to break some of the region, but you don't want the transfer of the load happens. At the same time, you don't want the deformation uniformly all across, right? You don't want this side to shrink as compared to this one, right? So you want a controlled deformation. Now, in order to do that, we can build a structure using 3D printing, and that was the challenge we started with. And we took this structure. Now, let me give 1 minute brief about what is the structure started from. Now, you take gold and copper, mix them in certain concentration, they undergo a decomposition, which end up resulting in structure which is shown here. Look at the scale, these are at nanoscale. The thickness of these are around 10, 50 nanometer and so. Now we take the structure, do a 3D scan, we can get this kind of complicated shape. We took this structure and print them. And we are able to print with a different thickness, hence we have different density. And what you see here at subscript is the density. Now, as you change density, you can see you can change mechanical property, you can change strength, you can change toughness, right? Now, that can be done with a 3D printer, and we have done all of it. We can nicely fit it and model it and tell it exactly which strength you want. We can print exactly that density. And you try to increase surface area also. So we take a cube, and effective surface area also can be increased. So we can increase how much surface you want, that also. And again, that correlates with the mechanical property. Having said, we try to understand why that happens, and all these are explained in the paper. But one of the most exciting part is as we build different density, we can stack them on top of each other. So we have a simple cube, and in the simple cube, we have different density structure printed together, different surface area printed together. We can select the region and put certain density. Okay, all these can be done, and with that we can show that when this cube undergo deformation, it can deform only certain region which we want. It can deform into certain direction depending on your requirement. All these can be done with a 3D printer. Okay. Now we can also build more complicated structure which are inspired by nanoscale, which has topology, and this some of these structures can make plastic or plastic-based material flexural strength, right? So you cannot really bend easily. Most of the plastic, any form you make, they have very poor flexural strength. We can introduce flexural strength, bending strength, and so on into the material, and the composite is what we have shown here. We can take the solid block and take out selectivity material, and most of the structures are built by mathematical model. And this is an example of Munger sponge, where the scientific Munger built this structure with a square or square porosity. He has built beautiful mathematical model to build this structure. If you look at 3D, this is how they look like. What we do here is try to modify the function. Rather than having a square, we made spherical, hexagonal, helical, and just changing the shape of the this porosity, we can modify its mechanical property. And the mechanical resistance can be localized, as well as directionality can be controlled, and we can do FEM model and exactly it can match. So if you have an object, we can put a model, and then the same thing can be printed with a selective deformation. Okay. And moving next quickly, printing high temperature material for aerospace, and some of them already took several cover pages. And we have here example of printing cement. I'm not going to discuss cement here, but I'm going to discuss graphene. Graphene being one of the most promising high temperature material or space material because of its high strength and the density and the flexibility, but putting them together is challenging. Some of you who are aware of graphite, putting them in shape is really complicated because it needs high temperature and higher processing condition. It's very difficult to build. Just hold on. Sorry, just a second. Yeah. Okay. So coming back to graphene, putting them together or even graphite, printing them is difficult. But if you take the graphite and put them into graphene, we can make an ink, and this is direct ink printing, where we can make a solution of graphene and then print them. We print them, try to understand its mechanics and how they print, and all these are detailed in the paper. We look at porosity, look at how when you deform the graphene printed block, how the deformation happen, all these are explained. One of the interesting observation, graphite is brittle, but if you take graphene and print the same solid block, it has a huge ductility. The specific reasons are explained in the paper. We do a detailed X-ray scan and try to understand the crack propagation, deformation mechanism, and so on. But interestingly, this ductility is not just once, right? You can keep on applying load under certain condition and it can replicate. All these details are there in the paper. I'm not going to go in detail. We can print using graphene complicated shape, and you can see all these shapes are printed here. We can build a mold and then pour metal into it, and we can get 3D printed metal blocks. So if you know conventional metal casting, as you cannot make very complicated molds, you cannot print them. But with 3D printing, we can make a mold and print any object possible. Now remember, these are graphene, so they are going to be conducting. So we can make conducting electrode of complicated shapes, which can help in several of the engineering material synthesis. Because graphene has good thermal conductivity, we can make a thermal conductor of graphene as well, which can help into some of this cooling activity as well. The details are there in the paper. I'll move next of 3D printing ceramic. So what we do is we 3D print ceramic, and then while printing, we coat with a very thin layer of polymer, and then we dissolve it. Now we have a material, we have a 3D printed ceramic with the interface where ceramic is diffused with a very thin carbon on top. And in general, ceramics are very brittle. And if you have a ceramic block or ceramic printed structure, you drop it and it breaks like this, right? Now, these are generally molded or casted by ceramic, and this is what happens. But now we are going to follow 3D printed structure, and because of 3D printing, adding a second layer on top of it, you keep on dropping the same ceramic, just processed with a different method involving 3D printing. You can see here, you can keep on dropping several times in different orientation, and it doesn't break. The reasons are explained in the paper, and the detail is provided. The whole idea here is, rather than just making ceramic, we make ceramic along with a ceramic reinforced with carbon. We are able to control or coat every surface so that it has certain strength. The material development is a big challenge. I talked about it. In most of the 3D printer, what you need is alloy, right? Powder. Powders are very crucial in metal printing. Now, if you don't get a powder of certain concentration or composition, you cannot print every material. And in powder making, early days, people were doing ball milling where they cannot really control shape of the particle. In 3D printing, if you are using laser based, the particle need to be of certain morphology and the size need to be very uniform. Otherwise, it's going to choke the nozzle. What we do here is we developed a printer, and these are all all these powder processing unit, which is commercially available, but they cannot really meet the requirement. Generally, they make a cluster of grains, but bigger particle from all the way smaller to bigger size with different morphology. We generally end up choking the nozzle. We developed a cryo mill where we take the powder to a low temperature and crush them with this ball mill. With that, we can make nano size. We can go all the way to 2 to 3 nanometer, make uniform size distribution with a spherical nice shape. And all these are already patented. We can utilize the same ball mill to recycle electronic waste and make a lot of phase control material as well. The reason why cryo mill helps is in normal milling. When you do normal room temperature milling, they end up getting fractured and welded together. Whereas cryo milling doesn't allow cold welding to happen or cold welding sintering to happen. You just have fracturing, and then the surface roughening or surface smoothing takes place, and finally you get as well separated, nicely shaped particles. This can be utilized in different applications. We have already built the mill, which is commercially available as well. The technology with us, it can be easily scale up in a different material synthesis or different processing condition as well. We can make all sorts of metal nanoparticles, ceramic nanoparticles, and we can make multi-component nanoparticles. What it means, you can take more than 1 or 2 elements, put them together, and this is 5 elements. We take them together, make an ingot, and crush them into nano size. You can see the nanoparticle of 50 nanometer or 50 nanometer, and so with a uniform composition of all 5 elements. So this is one of the beauty where you can control composition and print them precisely whatever composition you want. Our group does work on 2D materials where we make atomically thin materials like galanine, hematine, and graphene and related material. A lot of these took attention all over. In different journals, we can control phases, we can control physical and chemical properties, and utilize for energy and environment. We do work on developing new alloys where we develop microstructure and modify them with the composition and phase diagram. And finally, we look at its structure property correlation. That's another area our group work on. It's me, Chandrasekhar Tiwary. You can find me on ResearchGate, Facebook, LinkedIn, and this is our group website. Our group is consisting of very talented, postdocs, smart and hardworking PhD students, and couple of master and BTech students. We are always looking for motivated and excited researchers who are interested to collaborate with us and contribute to the research activity, what we do. With that, you can reach me to my email ID, which is listed here, my official email ID, and the Gmail as well is here. With that, thank you. We can take up question now.
Yes, sir.
I hope I was on time.
Yes, sir. Yes, sir.
Okay.
Thank you.
Now we can
Thank you very
take
much for
questions.
the wonderful session, sir. Now the session is open for the questions. The participants may raise their questions in chat box, and we have one or two questions in the chat box already, sir. Mr. Bhura Singh, are you available here?
Just hold on. Oh,
Mr. Bhura Singh?
oh, okay. Sorry. Okay, I missed these chats. Okay. Let me go one by one. Is it okay?
Yes, sir.
Okay. Okay. Fernando, are you around or he left? Derishon Fernando, if I'm spelling right. 11-12, he asked the question. I missed it. Okay. He says startup cost for 3D printing is about 100 in rupees. It will be 7,500. Is it's easy to look for trial and error method, right? I'm not very clear about the question.
Mr. Derrison?
The first question, Derison Fernando.
Yes, sir.
Okay.
Good afternoon.
Hi, Derison. You can
Hi,
ask the
sir.
question. I couldn't understand. So what you mean
Yeah,
by?
yeah. You differentiate between that myth and reality, right? That
Right,
tapered column.
right.
Yeah, you have told that that startup amount for that 3D printing is about $100. That's about 7,500 in Indian rupees, right?
Right.
But then it's okay to look for and that trial and error means if you are looking for that um, that model, right?
Yeah. Yeah, so that's what we do, right, in our lab also.
Mm.
When you build these computer models, right, and try to print them, there are going to be a lot of error while building the structure. And what we do is we take some of the cheap, and in our lab we have those cheap printers also. We print with a cheap polymer, print the structure, and see where is the error coming. Once we
Okay.
optimize that, then only we use the higher end printer,
First,
because then the same
first
material.
yes, sir. First, you will produce that a prototype model, right?
Exactly.
Yeah. After that, a final output.
Exactly.
Okay, sir. Okay, sir. Okay. Thank you so much.
Okay. Bhura Singh, sir, is this technology also feasible for metal element like titanium, etc., and is then how can handle residual stress? Oh, yes. Thank you, Bhura, for this question.
Good afternoon.
Yeah,
Yes, good afternoon, Professor. Could you hear me?
yeah, I can.
This was nice. I have one specific question. Since you talked much about something regarding the helmet, I want to go a little deeper. Any work regarding ejection seat to use in fighter aircraft to eject out? Any work, any
Uh,
idea?
we are very excited to work
Ejection.
in. Yeah. Uh, may I know who is speaking here?
I'm Professor Dr. Shankaran. I'm an air veteran, served in Indian Air Force. We do a peculiar problem, particularly for the MiG-21 or in generally any pilot rejection out. Even I witnessed in MiG-25 way back in 1980s, 42 years back. Generally what happened when they eject out, right, so where they land exactly we don't know. Generally they have a spontaneity problem, mostly they find ribs, nothing but the stress was very rightly said when you talk about the design of the so-called the helmet, bulletproof helmet, like that, the load, that fatigue load, when they jump from different altitude, right, the impact load is so high, so mostly they have a problem, mostly orthopedic, they say that is inevitable. Understood from the helmet concept, if you are in a position to make a better ejection seat, rather with this the present scenario, what you the research or what you are doing, it will be much helpful. We'll be able to get back so many pilots even if they happen to eject out. Thank you very much. I would like to hear the answer from you if any is going on
Okay.
research work. Thank
Okay.
you, Professor.
Thank you, Sankranji, and it's really
Also
delighted
great.
to. Yeah. Thank you, Dr. Sankranji. It's really nice to hear from well experienced people like you. Yes, the helmet problem. Yes, we are trying to do. We are researching on. In terms of the other problem, the the control or the interaction between fluid and material or this complex material is still complicated, and we are working in this area where we are trying to understand how fluid flow in this complicated shape. But we don't have any major program running, but it's just more basic research we are doing of because of our own interest. But yeah, if some of anyone is interested and working in the defense, if they want to interact, we are always open for any collaboration. Okay.
बहुत बहुत शुक्रिया है। लगता है आप घर से वर्किंग ऑन होम, इवन योर किड्स आपको किड्स कीप
Yeah.
डिस्टर्बिंग यू पापा पापा करके, बट स्टिल यू आर कंटिन्यूइंग योर वर्क।
Yeah, this is because we
मोटिवेट।
got we got a COVID cases in our department, so we have to clean
अच्छा,
the department and so on. So we are stuck at home. So the family, and especially if you have small kids, they're
yes,
always all
yes,
over you. Thank you so
but you
much.
are linking both profession and the personal. Somehow you are managing. Thanks a
Uh,
lot.
I
Very nice,
think
very nice, David. Very nice,
thank you,
David. Thank you,
thank you
Professor
so much,
Tiwari.
Uncle Ji. Thank you so much. Yeah.
Jai Hind, Jai Hind.
So Bura Singh, are you there?
Yes, sir. Yes, I'm there.
Yeah. So Bura Singh ji very nicely pointed out the question. Uh, yes, there are several, and even we can print titanium. But the problem, I'll just address first problem. We can print titanium, but only those titanium which we can make powder can be utilized till now. Okay. So the composition is restricted. You can only, until unless there are, you build your powder, so you make an alloy, then make a powder, then only you can print. That's the limitation. And yes, residual stress in metals is challenging. We do have a project on that, and what one of the way we do is we control the heat transfer, because any stress or shrinkage or porosity, and remember 3D printing using laser is nothing but a solidification process. And what we do is the heat transfer, if you can control solidification. So we are working with the thermal engineers or the guys who handle fluid and temperature. We are working with them so that we can control both of these and control stress and porosity. Okay. Please share feedback links. Okay. Please share feedback link. I'm not sure what about that. Selva
That's
Rajan.
for us, sir. That's for us, sir. Kindly leave
Okay.
that.
Uh, Era, thank you, Eraji. Very nice. Okay, I don't see any question.
Yeah, good afternoon, sir. This is Malik Prabhu.
Yeah.
Yes, sir, I have a question regarding the materials. And, sir, what would be the fatigue properties of aluminum-based materials, sir? Since in aircraft structures, mostly the structures fail due to fatigue.
Okay. And so, can we go a little slower just to understand which, like, you want to talk about solid structure or you're talking some specific porous structure?
Specific porous structures like in the wing, if you are using the aluminum-based material to 3D print, and if you are making a wing out of it, so how would be the fatigue properties, sir?
If I understood your question, see, the fatigue property is going to governed by the load you're using, right? Now, we are not claiming that 3D printing is going to extend the load and your aluminum will start replacing steel or nickel, right? Aluminum is going to replace solid aluminum, okay? And if the connects are fine, the load where your or the yield stress is good enough and your load what you're using is lower than that, there is no reason of fatigue property to change. Having said that, we have not measured fatigue property of specific objects under tension or compression, whatever. But the criteria for most of the design, if your material yield is way higher or your applied load is in elastic range, it's not going to affect fatigue. till certain cycle. But yes, there is no focused research with a porous material into fatigue area. We have seen cyclic study where you apply load and unload and look at for several cycles, but the conventional fatigue measurement on most of the structure is not done. One of the reason I'll tell you also, because most of the 3D printed structure, uh, especially for porous, the standards are not well defined. So most of our studies are lab scale. So talking about wings and printing them and trying to compare is something, the some of the structures are there in terms of windmill, right? So the big blade of windmill, they are made of composite. They do some of the fatigue study, but again, the inside porosity is way bigger than what we are talking about. So what we have done is not tested, and we are in the process in future to do it.
Okay, sir. Thank you, sir.
Okay, I do see a question by Natraj. What about the free energy of the system in such a case? How about the high entropy alloy by additive manufacturing? What about fatigue life material after additive manufacturing? Okay, Natraj, a very nice question. Thank you for asking the question. Yes, high entropy alloy can be printed now, because till now people are not able to make high entropy powders with the control composition. That was one of the restrictions. Now we can make high entropy powder with a control composition. There are several work around high entropy. People are printing it. Fatigue life, because under compression still okay, but as in 3D printing, you end up having a very small porosity. The best people talk about is even 0.1%. Now under tensile load, these are detrimental and not good in cyclic loading, which is fatigue. So that's a problem. People are trying to change it, and that's one of the challenge in the community. uh, Sir, can you share the fatigue property aluminum based use 3D printing is mostly failing due to fatigue? There are, I, it's not on top of my head, but I do remember seeing some of the paper where they take 3D printing and they have of aluminum alloy, and they have measured its fatigue property. There are papers. I don't remember on top of my head, but yes, you can drop an email and I can find it out and share with you. Any precipitate material is designed by additive manufacturing? Yes, Natraj, there are several precipitation based alloys like nickel based super alloy. They have printed, they have a precipitation, and they have seen additive manufacturing. After that, they do a treatment to get the precipitation and control the precipitates. Feedback. Okay, the feedback is not for me, right?
Sir, yes, sir. It is not for you. It's for the participants.
Okay.
We have one more question at the bottom, bottom of the chat.
Oh, whether shape memory alloys can be 3D printed, which process can be 3D printed? Okay. Manivel. Manivel ji, yes, we can, like shape memory alloy, the biggest problem is getting composition right? A small change in composition, the shape memory doesn't work. So there is a lot of effort. People are trying to make shape memory powders. I'm sure there are several suppliers who are able to make. If the powder is there, you can print. But the problem is, again, while printing, if you change the stoichiometry, it will have its own effect. And I'm sure the shape memory community, they do talk about that, and they're trying to work in that area, how to control composition and the printing conditions so that they can retain composition and microstructure so that they can get shape memory effect. But yes, it can be printed with laser feeder or powder bed as well as a powder feeder. Both can be utilized for shape memory alloy. We are also trying to do using for a small sensor application or actuator application, we are using direct ink as well. Okay. That's all. Any more questions?
Any more questions from the participants? Any more questions? You may please drop a message in the chat box, or else you can unmute your mic, please.
Thank you, Manivelji, for your kind words. Sorry, I couldn't read each of you. I do see a lot of messages. People are talking good thing about the talks, and I'm really thankful to all of you. The idea of this kind of interaction is not to just have a talk. All of you are very open to send an email and drop me anything, in your thoughts, or you want to have discussion. Feel free to do that. Okay. I have a meeting to catch up. So
Okay, okay, sir. Thank you,
we
sir.
can
So
we can
that
have
we can
another
conclude the
5 minutes and
session.
then I can leave.
Yes, yes, sir. Sir,
Okay.
out of curiosity, I have a question, sir. Can I
Yeah.
please?
Go ahead, please.
So you have shown that ant house and the shell structures.
Right.
And what is the major takeaway from that? The nature's creation. So that is the topology influences the strength of the material. Is that it, or anything else?
Okay. In just one line, you are very right. I'll make it little more generic. I'll not just say strength. Okay. Strength is just one designing criteria. Okay. I'll say mechanics. Okay, which is much broader, because you may have a compressive strength, but if you have a poor bending strength, you can't use it, right? The material. Stress is just one aspect. The fracture toughness, the load distribution, all these are crucial. So in one line, I'll just say topology controls mechanics. Okay, and that's the take home from the all bio-inspired structure what we have explored so far.
Okay, sir. Thank you so much, sir.
Okay.
So, on behalf of the Department of Aeronautical Engineering, I convey my sincere thanks and gratitude to you for being here and presenting a wonderful session. So we hope that the participants all around the country, those who are here, have gained a lot of knowledge and information from your presentation, sir. So thank you for accepting our invitation and giving a wonderful presentation. Once again, thank you very much, sir. Thank you for being here.
Thank you all. Take care and see you sometime once things opens up. Okay.
Yes, sir. Yes, sir.
Bye-bye.
Bye, sir. Thank you. Okay, once again, thank you, participants. Thank you for your participation. So I hope you have enjoyed the presentation, and don't forget to miss the last session, which is about to commence by 2:30 p.m. in the afternoon, and we have the last speaker for this 5-day faculty development program, Professor N. Venkateshwaran. He will be joining us from Rajalakshmi Engineering College, a professor of mechanical engineering, one of the eminent researcher in the top 2% scientist list from Stanford University. So we are looking forward to see you for the afternoon session. Until then, bye from here, Hindustan College of Engineering and Technology. Thank you so much for being here. See you soon.